list. And this is a small example for the case of n equal 5. Men are numbered as 1, 2, 3, 4, 5, and women are labeled as A, B, C, D, and E. And each row represents a preference list for each person. So from the preference is always from left to right. So the man 3 likes women, B, A, E, D, C in this order. And the purpose of the problem is to find a matching between men and women, like this. And for convenience, I use this representation to express a matching on a preference list. 1 is matched with D. So D is partner is 1. 2 to C, C to 2, and so on. But actually, this is not a feasible solution of this problem. So let's see the man 1 and the woman C. 1 and C, 1 prefers C to his partner D. And also, C prefers 1 to her partner 2. So if 1 and C are matched by ignoring the current matching, then both of them becomes better, right? So in this sense, we say that 1 and C is a blocking pair for this matching. And a matching that does not have any blocking pair is a stable matching. And the problem of the purpose of this problem is that for a given input to find a stable matching. And this is one example of the stable matching for the previous instance. You can see that this is stable. For example, for 3, he prefers B and A to the current partner. But both A and B are matched to the better man than 3, and so on. And this is another stable matching for the same instance. So the stable matching is not unique, not necessarily unique. There may be more than 2 stable matchings for one instance. And this problem is very old. Not very, but old. It was proposed by Gale and Shapley in 1962. This is a seminal paper. And I think that there are more than 500 papers concerning computer science, mathematics, economics, game theory, and so on. And this problem has, as you can guess, a lot of applications in real world. The most famous one is assigning medical students who graduated medical department of university to hospitals for training. And this, the stable matching is used for matching systems of hospital residents in these countries. And there are some, I think there are some other countries. Of course, there are good for school and student assignment problem. And there are some other applications. For example, scheduling algorithm on internet routers. Stable matching can be used to match between input ports and output ports. This is one application. And matchmaking of chess tournament or kidney exchange. I just briefly introduce a kidney exchange application. For example, some donor wants to give his kidney to, for example, to wife, but it does not fit, so you can't. And there are many such pairs. But if you exchange kidney, then this kidney can fit to this patient, and this kidney fit to this patient, then you exchange. And so the matching we find matching between such individuals to perform kidney exchange. So
why do you need the stable matching there?
Because, for example, if there's a blocking pair, then they want to do it each other. So, you know,
So,
if it's not stable, then if there is a broken pair, they complain.
in what sense? Do they have preferences?
Yes, for the how this, for example, this donor's kidney may fit to him or him, and the some kind of medical examination shows degree of fitness. And another interesting point is that you think that you can, it's not necessarily pair of matching. It could be cycle. For example, this donor can provide to this patient, this to this, this to this, and this to this. Then it's cycle. But the restriction is that you need to do the operation simultaneously for these 8 people. The reason is that once this donor gives a kidney to this patient, this guy has no incentive to provide kidney to this patient. So it should be done at once. So the short cycle is preferred. So basic questions are the following. Is there always a stable matching for any instance? So the answer is yes. For any instance, there is at least one stable matching. And as you see, it's not necessarily unique. And then in the computer science point of view, is it found easily, efficiently? And this is also yes. The Gale-Shapley algorithm, which I will show soon, can find it in order n square time. Again, n is the number of men and the number of women. So this is a linear time algorithm because the length of the preference list is n square. And here is the Gale-Shapley algorithm. I show an example. This is very simple. First, initially, all people are free. And choose any free man. Then let him propose to the first woman. The first, if a woman is currently free, she always accepts the proposal. Then take any man, go propose and receive proposal. Choose any man, go to C, and she receives 4, and next 5 goes to C. Now, just one woman received 2 proposals. Then she chooses the better one. So in this case, she rejects 4. And 4 becomes single again. And 4 deletes C from the list. So his top is now B. And we continue this procedure. Now, C rejects 5. And so on, until all people are matched. And the result is a stable matching. The proof is easy. I will show a sketch of the proof. Probably you may already found the proof. Just suppose that there is the matching is not stable, then there must be a broken pair. For example, 2 and E, right? And 2 proposes from the top of the list, and he is matched to this woman. So he must have proposed to E during the algorithm, but he was rejected for some reason. Why E rejected 2? Then E was already matched to a person better than 2. Or she received a new proposal better than 2. Anyway, after E rejects 2, she must be matched with a man better than 2. And after that, she may change partner, but get never worse. She always improve when she changes. So this cannot happen. So it's a contradiction. And in the original definition of the stable marriage problem, preference list must be strict and complete. This means that, for example, if there are 5 women, each man has to include all 5 women in the preference list in a strict order. But for example, in a real application, it's inconvenient. In a Japanese hospital student matching system, we have about 8,000 participants, students apply. So it's hard for each hospital to make a list including all of them. So there are 2 natural relaxations of preference lists. One is to allow ties in the preference lists. For example, this man too likes C and A best, but he is indifferent between those 2 girls. And then next B and E, and they are equally preferred by 2, and finally D. It's called stable marriage with ties, and I use SMT. And I use SM for the original stable marriage problem. And the next one, second one, is to allow incomplete preference lists. So in this relaxation, for example, the man too likes women C, A, E in this order. But he wants to be single. He would be rather single than to be matched with B or D. Yeah? In that case, 2 preference lists can be incomplete. And I use SMI for this problem. And from the next, I will show some known results for each of them. First, I consider stable marriage with ties. So the instance is like this. And I will make the definition clearer. For example, let us consider this matching. And then we define 5C as a blocking pair because, for the same reason, 5 and C can improve, both of them can improve the situation. But 1C is not a blocking pair in this definition. C can improve, but 1 remains the same. In that case, we don't say this is a blocking pair. This is we have many other definitions such that in which 1C is a blocking pair. But in this talk, the definition in this talk does not allow 1C to be a blocking pair. It's called weak stability. There are 2 other stability, strong stability and super stability. But in the again, in weak stability, both of them have to improve. And in this problem, SMI also, there is also always a stable matching for any instance. The proof is very easy. Let this be a given instance. Just break tie arbitrarily as you like. Then we have original SM instance without ties. And we already know that it has at least 1 stable matching. And it is not hard to see that this matching is also stable in the original instance. And so this gives a polynomial time algorithm. So it can be found, 1 can be found in polynomial time. The next one is SMI, incomplete preference list. So far, we considered only perfect matchings. If there are n men and n women, the matching size is always n. But this, in this relaxation, matching is not necessarily perfect. So we consider partial matchings. Okay, so let's consider this matching of size 3 to extend the definition of a blocking pair. 1C is a blocking pair in the same reason, for the same reason. And 4D is also a blocking pair. 4 can improve by matching with D, and D is currently single, but includes 4 in the preference list. So it's defined as a blocking pair. And the last one is a trivial blocking pair. Both 3 and A includes each other on the list, but both of them are single. This is also a blocking pair. And again, there is always a stable matching in SMI. Not necessarily perfect matching, but there's always a stable matching, and it can be found by a Gale-Shapley algorithm, just slightly modified Gale-Shapley algorithm. And there is another interesting property.
So I'm not too quick, I can't see. So if I have I can see that there's not necessarily perfect matching because maybe the system has no perfect matching, right?
Mm-hmm.
But if you have a perfect matching, how large partial stable matching can you find?
It depends on the preference.
So could I have a system that has just as a system it has a perfect matching, but
not necessarily stable, right?
Not necessarily stable, but the best stable matching, or a stable matching that is very, very small.
No, it's within a ratio of 2. You can see later. See it later. Of course, if we ignore stability, then we can have larger stable matchings, but it can be at most twice. So yeah, I go back to SMI instance. Okay, and this is a very interesting theorem. We can partition set of men M into M1 and M2, and W into W1 and W2, so that in all stable matchings, people in M1 and W1 are matched. M2 and W2 are single. No? The set of matched people and single people are the same for all stable matchings. And I will give a proof. Suppose M1 and M2 are the two stable matchings for the same instance, I. Like this. And we will construct a bipartite graph using, it's a union of M1 and M2. And so this is a bipartite graph, and the degree of each vertex is at most 2. Yes? So if the vertex has degree 0, it's okay, because he is single in both matchings. If the vertex has degree 2, then it's also okay. He or she has matched in both matchings. The problem is vertex is degree 1. And we want to show that there is no vertex of degree 1. It suffices to show that there is no path in this bipartite graph. Okay? And suppose there is a path like this. Because the man 1 is matched with A in M1, so his list must include A. Next, we move to A. Because A is matched with 1 in red matching, with 2 in blue matching. So she includes both 1 and 2. If 1 precedes 2, then in the blue matching, 1A is a blocking pair. So it must be the case that the order is 2, 1. Next, I move to the man 2. If A precedes B, then 2A is a blocking pair for red matching. So it must be the case that B is before A. Like this, we can determine the order of two persons in the preference list like this, and finally we get a contradiction in last part. 3C is a blocking pair in blue matching. So if there is a path, there must be at least one blocking pair on this path. So there must be no path. The connected component, all the components are cycles. So the theorem holds. And direct corollary of this theorem is that in SMI, all stable matchings have the same size because the set of matched people are the same. Yes. So far, we considered the original stable marriage problem, stable marriage with ties and with incomplete lists. We have already seen that all stable matchings have the same size. For the first two, stable matchings are always perfect matching. And finding one stable matching is easy. So the problem of finding a stable matching of maximum size is also easy. Just find any matching, it's maximum. And what happens if we allow both ties and incomplete list at the same time? This is an example of the problem SMTI. For this problem, this matching of size 2, this matching of size 3, and this matching of size 4 are all stable. So the situation completely changes. There can exist stable matchings of different sizes for one instance. So the problem of finding a maximum size stable matching is no more trivial. And we are interested in this problem. And here is a history. I'm involved in this problem for more than 10 years. And here is a list of results of our group and other groups for this problem. Here I will show upper bounds, positive results. And this part I show negative results. First, we proved in 1999 that the problem is NP hard. It was not known before that. And next, we proved that this problem is APX hard. That means that there's no 1 plus epsilon approximation algorithm. That means that this problem does not have p-tas. And C approximation means, probably you may already know, but C approximation means that for any input, the algorithm outputs a solution whose size is at least 1 over C of optimal. So the algorithm solution and the ratio of algorithm solution and optimal solution is always bounded by C. So if C is smaller, the algorithm is better. And the current best lower bounds are like this. If we assume P not NP, these are lower bounds. And if we assume unique games conjecture, these are lower bound. And I'm sorry. These are general result lower bound for general max SMTI. And these are results for max SMTI with one-sided ties. This means that, for example, women can include the ties in preference lists, but men's preference list must be strict. So this is a sub-problem of this problem. So this is easier. This is harder. Okay. And next, I show tractability, approximability results. First, approximation ratio of 2 is easy. I will explain soon. And the first improvement is in 2004. We slightly improved the approximation ratio, but it is still 2. it approaches to 2 when n goes infinity. And next, again, we slightly improved, but the progress was very small. And finally, in 2007, we got a ratio strictly better than 2.
This is the value of C? No, I don't understand. What is
This is C. Sorry, this C is not.
right. The 2 is the C.
Yes,
Yeah, okay.
2 approximation.
Yeah.
Now 1875 approximation algorithm. And other researchers presented better ratio for one-sided tie case. And after that, a guy from Hungary improved our result next year to 1667, it's 5/3. Actually, when I was working around here, I thought that the real approximation ratio is 2, like vertex cover problem. So I thought that we should try to raise lower bound, but yeah, but we succeeded. And so some other researchers tried to improve our ratio. So, and again, next year, the researcher from Glasgow, Scottish researcher improved it to 1.5. And of course, the upper bound for general case applies to the restricted case, so 1.5 applies also to McDermott result applies to this case. And this is the current situation. And in this problem, k plus 1 over k has a real special meaning, as you can see later, for integer k. For example, the trivial case 2 is 2 over 1, and 1.5 is 3 over 2, again 3 over 2. And for the lower bounds, 4 over 3 and 5 over 4. But this is a size of ratio of the alternating path, augmenting path. And we need some new idea to break upper bound or lower bound. And very recently, we were successful for improving one-sided restricted case. The progress is very small, 0.03. But it's important to break 1.5 bound, you know. So I'd like to, for the rest of this talk, I'd like to show some ideas of upper bound results. First, I show that the approximation of 2 is easy. So consider any, consider maximum stable matching, optimal matching of size S, and consider any matching of size less than half the optimal. Then there must be a pair of man and woman who are single in this matching. Both are single, but both are matched together in this optimal matching. Then by definition, this pair is a blocking pair, right? Because they write each other on preferences because they are matched here. So any matching whose size is less than optimal, less than half the optimal, cannot be stable. So arbitrarily stable matching has size at least half. And so find any matching, any stable matching, then it's a two approximation. And this answers to your previous. But not exactly, but yeah.
Okay, then I understand. Yes.
So next, I show this result, about this result. So from the previous observation, we can see that the worst case situation is like this. This is maximum stable matching, and blue is our current stable matching. Then we have ratio of 2. Then using this structure, we can somehow determine the order of order in preference list using the like the proof that there is no path. So our first idea is to increase the size by a local search type strategy. Just remove one edge and add 2 edges. And if this is stable, we are happy. And just try to remove some edge and add 2 edges. And if this is stable, again, we are happy. And our first attempt is to increase the size, keeping the stability from an arbitrarily stable matching. And unfortunately, we found a worst case example. This has a size 8, maximum size is 8. Our current size is 5. But we can extend it to n and n half plus 1. So we can go further from this matching. So this is a bad example for our first strategy. So this is our first strategy. We get a larger stable matching by addition and deletion of edges, but we failed it. And what we have done is to use intermediate matching. By removing and adding edges, we construct a matching mi prime. We modify mi to mi prime. Mi prime is not necessarily stable. This is the same thing, but yeah, mi prime is not necessarily stable, but it satisfies some good condition. I will show the condition later. And it has a larger size than mi. And if mi prime satisfies this good condition, then we can make it stable without decreasing the size. So we apply these 2 procedures repeatedly to get larger and larger stable matching. So I said we constructed 2 procedures, increase and stabilize, for these operations. And what's a good condition here? Because this matching is not necessarily stable, there might be a blocking pair. Our condition says that if MW is a blocking pair, either M is single or W is single. So this is not, this cannot happen. This is a prohibited blocking pair. Both M and W are matched case. And if there is a blocking pair, only M is matched and W is single, or W is matched, M is single, or both are single. The intuitive reason is that if there is this kind of blocking pair, we just change the partner of M from her to W. Then we don't decrease the size. But if such a blocking pair exists, we have to decrease the size to remove this blocking pair. Now, yeah, this is our strategy. We start from arbitrary stable matching. We apply increase and stabilize to get a larger and larger stable matchings. And we proved that the procedure stabilize never fails. And procedure increase may fail. But as long as matching size, current matching size is relatively small, almost half the optimal, then increase never fails. So we apply increase and stabilize repeatedly until increase fails. And output that current matching, then if the current matching must satisfy this inequality. From this we can get 1.875 upper bound. And in this talk I would like to show for the procedural increase. So I first define good edges. So as before, let this be an optimal matching, and this Mi be our current matching, and we overlap these two matchings. Yeah. And we consider the matching component of length 3 path that has 2 opt edges and 1 Mi edge. And we define the intermediate Mi edge of this component a good edge. I show why this is good later. So this is good, but these are bad. Now, because we are considering this case, so our current matching is almost half the optimal. There must be a lot of good edges because this component makes the ratio close to 2, right? And why good edges are good? So these red edges from opt, blue edges from Mi, our matching. First, if we want to remove 1 edge and add 2 edges, then blue edge is good for that reason, because at least A and 2 has at least one person who, that is 1 and B, who are currently single. So if we delete, remove this edge, then A and 2 can be matched. We don't know if it's stable, but anyhow we can match both A and 2, right? They can find partner. And next, we can prove that for either either 2 and 1 are tied in A's list, or A and B are tied in the man 2's list. If it's not the case, then the pass and the previous proof applies to show the contradiction. So we know that either for A or 2, the current partner and the optimal partner is in the same tie. This is a very good hint. Now, suppose that we don't know which one is good edge. This is the current matching. But suppose 3B is a good edge. Suppose that the person in the same tie is currently single, and suppose to change the partner of B to 8. Then, 8 becomes better because he was single, but now matched. B does not become worse. Of course, this 3 become worse because he is now single. But this guy does not create prohibited blocking pair because he's single now. It's allowed. So there may be a chance to match 3 to some person. And if this matching satisfies, does not have prohibited blocking pair, then we are done. But in general, it is not the case. But we know that there are a lot of good edges. So we do for each woman to draw an edge for single men, currently single men, who are in the same tie with the current partner. We do for all such women, because there are a lot of good edges. And find a maximum matching of this bipartite graph. Because there are a lot of good edges, we can guarantee the size of this matching. Then we change the partner of these girls, and they become better, and they does not become worse. So, and good points are that the matching size is the same. Yes, and no one here become worse. And many women change the partner, so there are a lot of chance to match new single man to some single woman. And if one of them is successful, then we are done. actually we need one more modification. I don't get into more detail, but we again modify the matching without decreasing the size. Then we can guarantee that there is at least one man such that by matching him to a single woman, we can have a matching with a desirable condition. Okay, so that's the idea of our 1.875 result, and I want to show 1.47 result idea, but this is an improvement of this. So I first show briefly this result. His result is for one-sided tight case. The algorithm is called GSA1. It's an extension of Gale-Shapley algorithm. In the Gale-Shapley algorithm, each man proposed to a woman only once. But in his algorithm, each man can propose to the same woman twice. This is an execution of Gale-Shapley algorithm to this instance. So suppose 2 goes to A. A receives a proposal. Next, 1 goes to A. But for A, this is not improvement. So A rejects 1. Next, 3 goes to A, but 3 is rejected for the same reason, and 3 goes to C, and C accepts 3. Even if 1 is single, he has no list, no more women on the list. So algorithm stops here. And Kirari's GSA1 is matching size is 2. Kirari's GSA1 is the same up to this point. And then if a man is single, then he is promoted. And he can have a second chance. So he goes to A. And a woman receives 2 proposals from one promoted and one unpromoted. She always selects promoted one. So 2 is rejected. Then 2 goes to B, and we have a matching of size 3. And it is guaranteed that the result is always stable.
Okay, so in the last step, 2 is promoted as well, right?
No, 2 is matched with B. If he is rejected by B also, then she will be promoted. And Kirari proved that after his algorithm, there is no this component. So the connected component that maximizes the ratio is this one. So the upper bound of 1.5 is guaranteed. However, there is a worst case example that gives 1.5. So lower bound example for his algorithm, GSA1. So to attack 1.5 upper, to break 1.5 upper bound, we need to attack this component, right? So I will, but I'm sorry, I almost consumed the time. So I will briefly show an idea of this algorithm. So this is a worst case example for Kirari's GSA1. I will show execution. 1 goes to A. Yes. 3 goes to B. 2 goes to A, but rejected. Next, 2 goes to B, but rejected. And then 2 is promoted, again goes to A, then he wins this time. And 1 becomes single, then 1 is promoted. 1 goes to A. But this time, both are promoted. So for A, 1's proposal is not an improvement. So she rejects 1. Then we have matching of size 2. But optimal size is 3. Oh, sorry. So what we want to do is to make 3 to propose to C. Then we have a size 3 matching. So what's the problem? When B receives proposals from 2 and 3, she selected 3. If she can reject 3, then 3 will go to C. But in Kirari's algorithm, it depends on the order of proposals. And we want to force B to select 2, always 2, without depending on the order of men's proposals. And here is our idea. In the Kirari's algorithm, he used 2 states, promoted and unpromoted. And Uman's decision is depends on these states. And we extended it so that each 0, 1, just 1 bit. We use values to show the strongness of each man. For that purpose, we use integer programming formulation of the stable marriage problem and its linear LP relaxation. And man with a larger value is stronger. This is integer programming formulation of stable marriage problem. I don't explain details, but we use variable xij for men I and woman j. If xij is 1, then I and j are matched. And we relax this condition to get a linear program relaxation. So xij can take any value between 0 and 1. And this value gives us some information that how much extent I and j should be matched in optimal matching. So we use this value to determine the woman's decision. Now, simply speaking, our strategy is like this. Suppose 1 and C are currently matched. And for example, 4 proposes to C, and they are in the same tie. Then we see the value of x1c and x4c. And in this case, x1c is larger. So the man 1 wins. C selects man 1, rejects 4, like that. But actually, the rule is much more complicated, and I can't explain detail here. But the idea is like that. And the effect of using that value to our case is that just consider this particular example. Then the unique solution for LP relaxation for this particular instance says that 1A, 2B, 3C, that's an optimal matching, is 1, and other values are 0. So if we apply that procedure to this instance, then we always get, without depending on the order of men's proposal, we always get an optimal matching. Of course, in general, the structure is much more complicated. So the effect of using the LP solution will be weakened. But we showed by calculation that even if the effect is weakened, but we can still have very small but a constant progress on the approximation ratio. Okay, yeah. Today, that's a summary of my talk. You all know, and this is a current upper bound and lower bound. This assumes not unique games conjecture but P not NP. We have this gap. So probably my next step is to apply this method for general case to reduce break 1.5 bound for the general instance. Thank you very much.
So do you expect that